This video is going to be about Bode plots. We're going to talk more about frequency analysis, and one of the good plots, a good way of representing that, is through a Bode plot. And it's fairly simplistic that you just have the different features of your transfer function plotted against frequency. What that means is that you'll have two subplots, magnitude and phase angle respectively, each versus frequency, and we plot these together. And when you talk about a Bode plot, you're actually talking about these two subplots plotted as a unit, just these two subplots versus frequency. And in this video, I want to show the standard formation of the transfer function once we move it over to the frequency domain, and then how to plot an estimate plot of the Bode plot using the different features, the zeros and the poles and the constant from your transfer function, and then the effect it has on these plots and how they look. So, one of the main uses that we're going to use with Bode plots is to first plot all of this information, and then we can use that to form a Nyquist plot, which is really the magnitude versus the phase angle. So we use all of the information that we form here, we draw a polar plot, and then based on the Nyquist criterion, we can establish if that system, using the open loop information, is stable or not for the closed loop system. So that's really useful. All right, so far we have been talking about transfer functions with respect to the S domain. And it was really handy for us to take something from the time domain, use the Laplace transform, and bring it over to that S domain, and then that saved us from having to do a lot of integration and derivation. They were reduced to just multiplication and division, so that was really nice to work with. But if I look at this, I can't easily say what the frequency information is typically. So what I want to do is reveal that information by making a substitution that S equals j omega. So I make that substitution, and now I'll have a transfer function that is g of j omega. And we can view this as two separate parts. It's going to have a real part and an imaginary part. And we can also view that as two separate functions. Let's call that r and x. And so the entire g of j omega is completely described by these two functions here. We'll have a magnitude and a phase angle if we take the angle and the absolute value. We'll get into those formulas just momentarily. G of j omega can also be written out with this magnitude and this phase angle in this formation. And then that describes our magnitude and phase angle, like so. Okay. So the formulas for calculating these different parts right here are square rooting each part of these functions right here, and then, squaring them and then taking the square root. That will give you the magnitude. And then the phase angle can be found by taking the inverse tangent of these two parts of the functions. And so you can always do calculations this way. It would tend to be a little more tedious for the Bode plots. It's much better to just do the estimate plots, the techniques that I'm about to show you. But you can always come back to this if you ever need to. Okay, so let's talk about how the Bode plots look. So we will have two plots together, and we like to plot the magnitude and the phase angle together like this, both versus frequency, and as much as possible try and match these frequencies up so that you can line them up and extract the information easily. I like to use a log scale for the omega axis, and then these will be in dB for the magnitude, and then degrees for the phase angle. So if you've never used a log scale before, what you want to do is try and take these decades by 10 and make them evenly spaced apart. So you'll start your plot, of course, at 0, omega equals 0. And then as you go along, start at 0.1 will be your first tick mark, and then 1, and then 10, and then 100, and 1000, and so forth, increasing by factors of 10. These individual parts of the graph, these segments, are referred to as a decade. And so we'll have some information that occurs over a decade. And so that's really how this looks. And so what if we had a 0 that happens somewhere in here? We would just mark this on the plot. It would happen in this decade, and that's fine. Just try to be as neat as possible, and then that really helps you a lot. Now, I'm using a pen to show up a little better, but I would recommend using a pencil for drawing the Bode plots, because as we build up the information, it's additive, and you might find yourself erasing a little part and redrawing it as you add more information to your plot as you go along. Okay, so let's talk about the standard form for the Bode plot first. Standard form for the transfer function that will then allow us to draw the Bode plot. So let me give you an example of the standard form. It will look something like this, and I've tried to add in 2 poles and 2 zeros up here just so we can have kind of a variety of representation here. So the standard form is going to have all of our critical frequencies, our poles and our zeros, happen with these divisors right here. So we're going to have this formula where we have our constant out front, and then this would be a 0 that happens at the origin, and then every other frequency, that a critical frequency elsewhere, we want to have a +1, and then divided by whatever that critical frequency is. Now, if you think about this in terms of frequency must be positive, then our critical frequencies happen when this omega equals this value right here, and then we would echo the 1. We would have a J, of course, but we would echo that 1 right there. So for this specific example, we would have poles at 150 and 400. We would have zeros at 0, the origin, and then we would have 1 at 2. And you might be thinking, well, that's not divided by 0, thankfully. That's not divided by 0, so why is it at the origin? Well, we're looking for that +1. If we have the +1, then we're in the correct form, and the +1 signals this is not at the origin. Look at this value. Okay, now what if I had a divided by 2 right here? Well, it wouldn't exactly be in standard form. We'd need to pull that 2 out and combine it with our constant. You can't do that here. This is a separate part of the equation, but if we're just talking about if we had a divisor by 2 right here, it was J omega divided by 2, you would pull that 2 out and combine it with your constant. Okay, so you want to have this kind of a formula. Okay, so let's talk about like having an example, and I've already kind of worked it out here. So this is an example of I did not start in the standard form. I have made this substitution of J omega, and I end up with something like this. And you can see I have 1 0 and 1 pole, but it's not immediately obvious what they are. I have to do a little bit of calculation first. So what I want to do is isolate one part and then try and formulate it in this kind of style that looks like the standard form here. So most of the time what you're going to do is take this value and divide by it, divide both parts, and then multiply. That effectively is multiplying by 1. So let's say we had the 10 j omega up here at the top. What I would do is I'd divide both sides like I've done here by 25. That leaves me with a +1 and a 10 divided by 25 here. And I, of course, need to multiply by the 25, so I'm effectively not changing the problem. Just changing the way it looks. Okay, so we'll do that for the top. So I've done that. And you multiply by the 25. And then also for the bottom, you divide by 50. And so we're left here. So we've got a little more simplification to do at this stage. But it's very convenient. I'd recommend waiting until the last part right here, last step or so, to combine your constant, because you will have these values right here to combine with them. Okay, so we take the 400, we divide it by 50, and we're left with 8. And then we multiply that by 25, we're left with 200. And then this is what we're left with at this step. Now, I really would like to have the divide by something, the j omega over something. And so what I did is divide by the 5/2. So you can view this as the reciprocal. It's kind of going backwards from what you normally do. But if I divided by 5/2, well, that's really the same as multiplying by 2/5. Okay, so this is now in the standard form, and I can work with it. And I can look at this, and I can easily identify this is my constant, 200. This is a 0, 5/2. And then this is a pole at 10. So these values are critical frequencies for me, and this is my constant. These will all affect the Bode plot. So let's get into how the Bode plot looks versus all of these different features that might happen. Okay, so first of all, talking about a constant. So let's say we had a function that is just g of j omega equals 3. So it's not really interesting, but I want to highlight what happens here. We want to convert this to dB. So for the magnitude plot, we would take the constant and plug it into this formula to convert to dB. This will give us a dB value. Okay, so plug it into 20 log base 10, and we take that, plug in the 3 for the constant, and we have, so it's similar to about 9.5. So that's where we would start our plot at. Now, nothing else happens for this particular transfer function, so it just stays that value for all frequencies. And for the constant, for the phase plot, the constant value doesn't really affect it at all unless it has a negative sign. The negative sign just represents the negative 180 degree shift, which you expect, right? If we think about our real and imaginary plot at our axis, if we went all the way over here, this is negative 180 degrees right over here. So a negative sign can be represented that way. If the constant's positive, we do nothing, which in this case, for this specific example, we just stay at 0 degrees. We have no other information to go off of, and so that's the only feature. And this is our completed Bode plot then for this g of j omega equals 3. Okay, so it's pretty simplistic, but these are really the only effects that you'll have. First of all, calculate constant, change it to dB, and then with the phase, it has no effect if it's positive, negative 180 degrees if it's negative. And there's that. Okay, so let's talk about zeros and poles that happen at the origin, because those behave a little bit differently. Okay, so say we have a 0 at the origin. In the magnitude plot, remember how we have these decades right here? Well, they don't really matter for the magnitude plot in this case. We would have whatever constant we started out with, and it would have a +1 slope, so, or a 20 dB per decade increase. So I can go ahead and make notches on the magnitude plot. And let's say that we have 10 dB, 20 dB, 30 dB, and so forth. I'm not going to worry about this small part right here because the frequency, the tenths and below of the frequencies don't tend to affect the plot very much. And again, we are drawing approximation plots. They're not going to be exact, but the overall shape should be pretty much the same as one you did in MATLAB or with some other graphing program. So the magnitude plot, we would, let's say we started out at a dB of 10, and that's where our constant had us originating. We would increase up to the 30 over this decade. Now they don't matter too much from them, you just want to keep the exact same slope, if that's all the information. So for this plot, that's going to be all the information that I have. That's my completed transfer function. So it has a +1 slope or a +20 dB per decade slope increase. It just keeps going. We keep that slope as frequency goes on. I almost said as time goes on, but as frequency increases, we keep that slope. Okay, so that's not really true for the phase plot though. We have that immediate +90° shift. If we have a 0 at the origin, we implied an immediate +90° shift. And once we do that, that's not going to change. We're not going to keep increasing the phase as frequency goes on. And again, that is only if there's no other features for this plot. Here I'm just trying to isolate each thing so I can show you what happens. But oftentimes we'll have something else happen, and so this line will change. Okay, so a pole at the origin. So I like to think about it, you have zeros on top on the numerator, and then you have the poles on the denominator. Well, zeros cause an increase both in slope and in phase shift. Poles have the opposite effect, and they cause a decrease. Similar effect, but negative. So we would have, let's say again, we started off at that 10 dB. So I have my 20 and 30, it won't matter too much. I will then have a -10 dB. And you can have negative magnitude. You can have negative phase and negative magnitude. A lot of the times you won't have a completely negative magnitude Bode plot, but it can go negative. So we would go, again, we will ignore this little part right here, just because we're doing an approximation plot and this doesn't factor too much. So over this decade, we would then decrease, and we would say this is a -1 slope or -20 dB per decade. And so if nothing else happens in this transfer function, if this is all we have, we would just keep decreasing. Now, it's important to note that with the magnitude plot, we are going negative values because we're dealing with dB. I forgot to mention that just a moment ago. Obviously, you're not going to have a magnitude that is negative by itself without a phase shift. So these two plots combined tell the entire story, just to be completely clear on that. All right, so back to this 90-degree phase shift. It happens immediately. So I'm saying we started out at 0. I'm going to say that for this example, we had nothing else affecting this plot. So the only effect comes from our pole at the origin. So we'll just draw that -90 degrees. If nothing else happens, this is our phase part of our Bode plot. So G of J omega up here, labeling that, and J omega. Okay. All right, so that's how zeros and poles affect you at the origin for your Bode plot. Now, zeros and poles can obviously happen at other places, so let's talk about that next. So say, in these examples, I'm just going to say, like, we have omega sub c be a critical frequency that is either our pole or our zero that we're talking about. It happens at a specific omega value, and so this is going to be basically our pole or zero, the frequency it happens at. Okay, so for our magnitude, we have a zero at some place, some omega c. The magnitude at that point, let's say it happens at omega c equals 5. So it would happen somewhere around here. So at that specific frequency, we have a +1 slope. So if nothing else is happening, and I just start out with a 0 magnitude, at that specific point, I will start to have this +1 slope. And that will be at again, a +20 dB per decade. And I didn't draw the y-axis yet, so right around here, that would be about 10 dB. Again, these are approximations. Now if I had the 100 out here, we would see that if this is 10 dB, by the time it reaches the end of this decade, then a +20 increase over the next decade would lead us to having a 30 dB value. So I'll just fill that in there. Okay, so for the phase shift, in the span of a decade, whereas with the magnitude plot, it just happens immediately, and that's really the only effect that we see. With the phase shift, this happens over the span of a decade. And so at the critical frequency, we have halfway of this shift. No matter what it is, our approximation plots will be drawn this way, where we have half of this effect of the phase shift. Again, 0 does increase the phase by 90 degrees, but if it's not at the origin, then it has to happen over the span of a decade. So we have a +45 degrees that happen at this omega c. So we know that we're going to be here. And then at 1/10 of it and 10 times it, or 1/10 of the overall frequency that the end of this decade is what I mean to say. The end of the decade and the beginning of the decade and the end of the decade, we finish out this effect. So I started here at 0 degrees. I didn't have anything else going on for this transfer function. And if you're paying attention, you'll notice that this is not a case that can actually happen because it's a 0 by itself, no pole, and we don't do that in the physical world. So yes, this is a very specific example, but I'm just trying to show you the effect. 0 degrees is where we start out at, and then we reach this decade. And then this is where we will start our overall increase. We will reach 45 degrees, halfway of the effect, by the time we're at omega sub c. And at the end of the decade, we should have our full effect of +90 degrees. Okay, if nothing else happens for this plot, it just stays that way. It just stays at +90 degrees. Okay, so the pole effects are going to be extremely similar again, but negative. So the magnitude plot, let's say we have omega c equals, let's say, that was really good to be in this middle decade. So I'm going to say that that's 8, for example. And so this is over here, and mark it down here on our phase plot as well. So a -1 slope. So if I started at 0 dB, then I would go ahead and decrease. There would be a little bit of information, so I might have to do a calculation to get this value. But over the next decade, let's say the 10 to 100 decade, then this, whatever this value was, we would decrease it by 20 dB. So let's say that, for example, we ended up with a -2 dB at this point, at the end of this decade that the critical frequency fell in, then we would decrease. This would be a -22 by the time we were at the end of the 100 decade. And if nothing else happens, it would continue on that way. Okay, for the phase shift, again, we have that over a decade, not instantaneously, like for the magnitude plot. So the magnitude plot shape looked like this. The phase plot looks like this, where we will reach that -45 degrees, and we also have to have the -90 degrees in here, and here. So I have nothing else for this transfer function. Let's say this is the only thing making sense, or this is the only part that we need to make sense to graph. So this right here, and then we just connect these dots. And if you want to, you can use the dotted lines to illustrate the decade. Now nothing else happens, so we have -90 degrees is where the phase shift stays. Okay, so this is our magnitude plot. This is our phase shift plot. Now, unless I ask for these values specifically, you don't have to draw them unless you just want to. If you want to be more precise, that's completely welcome. These calculated values like we were talking about up here. Okay. But everything like the -45, the 90, the phases that you end up with, the dBs, where you start from and where you build up to, try to be able to show those on your plot. Okay, so we're at a point where we can do an example. Okay, so this is going to be additive. And note that we might have to redraw it a few times. But let's do some examples where we have different poles, different zeros, and such. Okay, so I have a G of j omega, and I'm going to start out with using that 3 is our constant. We'll have a 0 that happens at, let's say, 15, and then we'll have a pole that happens at, let's say, 40. And then I'm also going to have another pole that happens at the origin. Okay, so this is going to be my transfer function right here. And I want to do the magnitude part of the Bode plot and also the phase angle part. Okay, so let's go ahead and draw in our log axis. Try and keep them lined up. It's kind of hard sometimes, but just do the best you can. Alright, so I think that's as much information as we'll need to know. Well, actually, let's go ahead and put in 1,000 as well. Okay, so first thing I do before I even start drawing is I want to identify what parts are going to affect our graph. We have a constant 3. We have a 0 at 15. We have a pole at the origin. And then we have a pole at 40. Okay. All right, so let's start out with the constant 3. We used this before, and we know now that the decade, or the dB value, is going to be somewhere around 9.5. So I can go ahead and mark that on the plot here. So it's going to be really close to this, 9.5. That's where I start out at. And the constant is positive, so it has no effect on our phase. And so I effectively could start out at 0 degrees. I do know that this is not going to be where we actually start out because we have that pole at the origin. So I'm not going to mark this graph just yet, but you could if you're using a pencil and just build it up. Now for the constant, this is really all that we have going on so far. All we need to do for our magnitude plot. And again, no effect for our phase plot. Let's try doing the origin, the pole of the origin next. So let's do them in this order. So these are going to be the steps that we add to our plots. Okay, so pole of the origin. What does that do? Well, that actually causes a -1 shift, or a -20 dB per decade shift on our magnitude plot. So this is almost 10, and remember, this segment right here, we don't really count very much. It doesn't have very much effect. So what we would do is effectively we would reach the -10, somewhere really close to that, as we went across this first decade. So it's somewhere around -10. Now I'm going to call it -10 just because it's going to be fairly close. Okay. If nothing else happens for our plot, then this is the kind of shape it would stay at. It would continue to go down and have that negative slope. So the pole of the origin actually has a big shift, -90 degree shift for our phase plot. So what we can do is just immediately we can draw in that -90 degree shift. Okay, so now we've taken care of the constant at 3, the pole at the origin. Our next item is the 0 at 15. So I'm going to go ahead and mark that 15 right here. And right here. Okay, so for the magnitude plot, we know that the 0 is going to increase the slope. It doesn't matter where it is, but it is going to increase the slope with a +1 slope, or a plus 20 dB per decade. So knowing that we have this negative slope, if we have a positive slope later, it's actually going to cancel it out. Now, if we had 2 zeros happening here, we would see a positive slope again. But you see how we have a -1 slope. And if we add in a +1 slope, well, it's just going to flatten that line. So I drew this a little bit steep, but we're not actually changing value. I'm just trying to keep the graphs from coming together. So this is still -1, and then at the 15 point, it just stays put. Now I know I have nothing happening until 40, so I can move a little ways until we have that 40 right there and have no effect. Okay, so hopefully that makes sense, where we just canceled out the slopes. We had a pole and a 0, negative slope, positive slope, so that leaves us with a slope of 0, at least until our next critical frequency. Let's go ahead and fill out the phase plot part of the plot, and then we'll come up here and do our last pole. Okay, so the 0 at 15, that means that I have to have half of this effect. 0 has a +90 degree shift. Half of that effect has to happen at that frequency, or by that time. So I'm going to go up by 90 degrees. And so that means I have to be at negative 45 degrees by the time I'm at omega equals 15. Okay, so I'm going to start my effect at the beginning of this decade and then finish at the end of the decade. So that means that I will go up just like that. And if there's no more information, this would just continue on at 0. Okay? All right, so we've taken care of that 0 at 15. The pole at 40. Okay, so here's where it's really good to use a pencil. The pole at 40, that would cause a negative slope. So it's a pole. It has a negative slope on the magnitude plot, -1. So after that point, we would have a -1 slope, or minus 20 dB per decade. Okay, so from 40 to 100, we would have a little bit of effect right here. And then from 100 to 1,000, we'd make sure that we had, if we were given this value right here at 100, then we would have this -20 on the y-axis of whatever that was. So just for example, right here, I'm going to say that this actually turns out to be -15 at that point. It won't, clearly, but just so that I have numbers up here, I'm going to estimate it. And then that means over this next decade, from the 100 to the 1,000, that I would decrease by 20 more, so -35 dB. Okay, so that's all the information we have for our transfer function, and our magnitude portion of the Bode plot is complete. So the pole at 40, mark that right there. So it actually needs to have half of the effect, which is a decrease of 90 degrees. Half of that effect has to happen at 40. And by the end of the decade, well, we have to be finished. So we have to have the full minus 90 degree shift. So what's going to happen is, since we have two critical frequencies in here, they kind of balance each other out. Let's deal back with this decade, 10 to 100. And so what's going to happen is we went up by 45 degrees. I'm not going to cancel that out, but I am going to connect it over and have, let's say it continued to increase and now it has to decrease. So we have again our -90, -45, and -90. So this line right here is going to be our Bode plot. So our Bode plot doesn't actually go up here. It goes up and then down and back to -90. Okay, so again, if you plotted this in MATLAB, it might look a little bit different, but you should see overall that basically the shape is similar. Okay, so now we've finished that as well. Let's do an example that's a little bit simpler, where we don't have so much happening in the same decade. Now this happens sometimes, but just for the sake of illustration, let's do an example of g of j omega, and let's say that I have some kind of a constant. I'm going to say that this is alpha, so that I don't have to calculate this right now. But alpha is our constant, and then we have a 0 at the origin, j omega, and then I'm going to have a pole at, let's say, 150. So these are very spaced out. This is a more simple example. Okay, so we'll get our two plots out, and then draw our axis in. Trying very hard to keep them lined up. and then label our axes. Just like so. Okay, so before I start drawing, I want to call out the different pieces here. I'm going to say that we have a constant alpha. Obviously we have a constant alpha, but I'm going to say that once we do the calculation, 20 log base 10 of alpha, that this is actually equal to 15. And then we have the 0 at the origin, and we have the pole at 150. That's omega equals 150. Okay, so let's get started. The constant, once we do the calculation and everything with the dB, we have 15. We can label that. I'm going to say 15 is here, and 20 is here, and 40 is here. And so alpha, I'm going to say alpha was greater than 0, so it has no effect on our phase plot at all. But it does affect our magnitude plot. It gives us that starting magnitude. Okay, so this is where we'd start out. Okay, so we've taken care of the constant here. Has effect here, gives us our starting magnitude, no effect on the phase plot. Now, for the 0 at the origin, that gives us an immediate plus 20 dB per decade or plus 1 slope since we're dealing with a log plot. We don't really have too much here, so I'm just going to go ahead and increase that there, plus 1. And so this is very, at the end of the 1 decade, it's going to be very similar to about 35. That was a plus 20 increase over this 0.1 to 1 decade, this first decade. And it's true that there will be a little bit of increase once we get to the 0.1, because there is a little bit of frequency here information. So it won't be exactly 35, but we're doing an estimate plot and it's going to be pretty close. Okay, for the phase plot, 0 at the origin, anything at the origin causes an immediate phase shift. It's 0, so it's positive. It's a 0, not a pole. Zeros are on the top. They have a positive shift. Okay, 90 degrees right there. Okay, so that just continues on until we have more information. Okay, so we've taken care of the 0 at the origin. Now the pole at omega equals 150. Okay, let's mark the 150. I'm going to say it's somewhere around here. Okay, so now this is a pole that is not at the origin, so we have to use that decade. Okay, not so much for the magnitude plot, but for the phase plot certainly. So I'm going to go ahead and continue the magnitude plot all the way out here to 150. Now, the pole gives us a -1 shift or a minus 20 dB per decade. And since we already had that plus 1, it just levels out. Our slope is now 0. We had a plus 1. We've added a -1 slope. And so we have the 0. 0 slope, that is. Okay, so that's what our finished magnitude Bode plot looks like. For the phase plot, we have to achieve half of the effect of our pole at the time, at the frequency that it happens at. So that's 45 degrees because we have to decrease by 45. So the pole causes that minus 90 shift overall, but we're doing it across the decade. So we'll have a 0. We know we're going to be completely minus 90 degrees or shifted minus 90 degrees at the end of the decade. We were already at 90. Let's continue this line till the start of the decade and then decrease just like that. And And then from this point onward, since there is no more information, nothing else to graph, it stays at 0 degrees. Okay, and that's our completed estimate Bode plot for the phase. And so that altogether is our completed estimate Bode plots set for this particular transfer function. So I hope that those examples helped, and these cover the first 2 problems in your homework set number 8, which is our last homework set. And there is a separate video where I'm doing problems that are exactly similar to homework set number 8, so you can view that as well if you want more examples. But there you go.